Good afternoon all. So wait for one more minute and then start the live session. We'll wait for more students to join. Till then we'll see what's the last week recap. So last week what we did is that we went through some of the concepts from the week 3 that includes ideal gas equations, numericals and tutorial problems as well as assignment problems related to the ideal gas equation of state. And we've seen some of the numericals as well as the concepts related to the Maxwell relationships, thermodynamic property relationships, and different terms like isentropic, isometric, uh, isobaric, and isothermal, and it's all the numericals based on these terms. And we also solved some of the numericals as well as the tutorials from the assignments of week 1 and week 2. So this is week 4. So what we'll do is we will go into deep into the apart from the ideal gas equation of states, there are non-ideal gas equation of states because all the real world problems are going to be non-ideal. So for that, all non-ideal problems that are going to happen in the chemical process industries, petrochemical refineries, agricultural industries, and pulp and paper fiber. There are so many chemical industries in which all the problems are non-ideal. So what I have to do is that we have to solve that problem considering the volume fraction, that is the volume occupied by the system, and the various constants related to that. So for that we will go to the non-ideal equation of states that relates that the problem we are going to solve is non-ideal. That is not an ideal problem, it is non-ideal. That's why it's termed as a non-ideality. So there are two different types of equations, that is non-ideal gas and non-ideal liquids. So we are going to see here now is non-ideal liquids and the corresponding equation of states. So last week I mentioned like there are 4 different non-ideal gas equation of states. That is, we'll start from the first one, that is the basic one in non-ideal gas, that is Van der Waals equation of state, which have 2 different constants like called as the Van der Waals constants A and B, which accounts for the attractive and the volume fraction in the system. The second one is Pang-Robinson, the third is Redlich-Kwong, and the fourth one is Redlich-Kwong. So each of these non-ideal equation of states will have the corresponding equations and the corresponding parameters. The parameter here corresponds to the 2 constants A and B, which accounts for the attractive forces and as well as the volume fraction occupied by the system. So whereas in the ideal gas, we assume that the volume is uniform, whereas in the real world volume is not uniform, it changes according to the processes. So that's why these 2 are the constants which will appear in in all of the non-ideal gas equations. That is the 4 one that I will state. Okay, so we'll see these 4 non-ideal equation of states, we'll solve some of the numerical problems, and we'll go through some of the concepts covered during this week. Sorry. So the already 3, so let's start with the week 4 live interactive session. So welcome you all the students on this course on chemical engineering thermodynamics offered on NPTEL from SWAM and NPTEL. So this is the week 4, a little bit just starting by the course. So this course has been offered by Professor Gargi Das. She is a professor in the Department of Chemical Engineering at IIT Kharagpur. And like I said, I will be your teaching assistant for this live interactive sessions for the entire course duration from Jan to April. So we're taking all the live interactive sessions on every Saturday from 3 to 5, so that we can like interact with the students if they have any issues related or have any problems related to the assignments, tutorials, or some of the concepts that has been covered during the entire week. So we'll try to cover up that up and try to rectify that issues within that week itself. So a little bit about myself, I'm just teaching assistant. I'm Rajput Shiva Majid Kumar, PMR scholar in the Department of Chemical Engineering at IIT Madras. Okay, so we quickly begin with the week 4. So we have already gone through the 3 weeks. So like I said, this is week 4, and in the week 1, week 2, week 3 we have covered starting from the scratch of this like basics of the chemical and thermodynamics. We have started from what is thermodynamics, why thermodynamics is important in chemical engineering, and the laws of thermodynamics like zeroth law, first law, second law, and third law, and various different terms like isobaric, isentropic, isothermal, adiabatic. And related to that, we have gone to week 2 and week 3, which cover the thermodynamic property relationships, Maxwell relationships, thermodynamic web, And then some of in the week 3 we went through the ideal gas equation of states and some of the numerical problems related to that. So in the week 4 the content is like this. So the first one which talks about the property estimation for the PVT behavior. So in the last week, in the week 3, I have shown you like the two different plots which corresponds to the PVT diagram of any fluids, like a perfect pure fluid or an ideal fluid. So if you see, in the last week, I've shown a plot like this. So if you have and like this, so these three different curves, okay. So it will come like this and will come. So it will solve as a sublimation curve. So there will be three different curves: sublimation, liquefaction, and it is the triple point or the critical point T, and this is the critical point above which all the phases will be gas. So this is what we have covered in the last week, like the PVT behavior of the pure fluids, and similarly you have also seen the PVT behavior of an ideal gas. So what is this is like the property estimation. So how are we able to identify the properties and how they can be estimated from the PVT behavior of any system that has been given to you. And the second one is the concept of chemical potential. This is already we have discovered, that is chemical potential. So the driving force, suppose like I said, if I have a container like this, and then this is a membrane that is separated, okay. So this is, suppose, is a membrane. This is gas A and this is gas B. So right now the gas A and gas B are separated by a membrane. So what will happen if I remove this membrane is that the gas A and gas B molecules try to diffuse into each other, and they will try to diffuse at a time until the time reaches which is known as the equilibrium value. So this diffusion will happen according to a term which is known as the potential. So the driving force is the potential, and that is the chemical potential within this species, which will try to accumulate. So once I remove this, what will happen is that the cylinder will become like a uniform, which will have a uniform mixture of gas A plus B after I remove this membrane. Okay, so this is what the driving force for this is, chemical potential. Okay, so this is the driving force. Okay, so this is the simplest for is the chemical potential, and that we can be derived in the thermodynamic terms, in terms of concepts related to the chemical engineering. Okay, so we will quickly begin with some of the non-ideal equation of states. So the first one that I mentioned up here is known as the van der Waals equation of state. So the ideal gas equation of state is given by PV equal to nRT, where we know that P is the pressure, V is the volume, N is the number of the moles of the ideal gas, R is the universal gas constant, and T is the temperature in Kelvin. So we know these things, but in real world, well, like I said, the volume occupied by the system will not be uniform. It will not be the same. So it changes according to the processes. Apart from that, the another term is the attractive forces. So the two molecules will try to attract and repel each other. So that accounts for different forces. So these two things has to be taken into account in the real world problems. And then therefore the scientists have developed like 4 different non-ideal gas equation of states. So what EOS is equation of states actually. So the first one, it talks about the van der Waals equation of state. So if you see, like I have mentioned of an equation here. So for the PVT behavior of a real gas, like I said, for the real world problem, this is the actual equation of state, that is called van der Waals equation of state. So P plus A by V square, V minus B equal to RT. Okay, so now there are two different terms here, A and B. So this accounts for the van der Waals constants actually. So you can see it's known as the van der Waals constants, and A and B values are been given up here. So this is, so what I'm saying is that you don't have to mug up these values, but this can be also be derived. So these are all derived values from the fundamental properties relations, and this is not just, so this equation comes from this one only. This is the ideal gas equation of state. So they will take two. So in ideal gas we assume that there are no attractive forces and the volume occupied is uniform, whereas in non-ideal gases what will happen is the attractive forces will be there between the two gas molecules, as well as there will be some volume expansion or contraction will be happening. So this accounts for the two different constants, that is called van der Waals constants A and B, which accounts for the attractive and the volumetric expansion or contraction into the system. So this is first van der Waals equation of state for the non-ideal gases. The second one corresponds to the Redlich-Kwong equation of state and Sawyer-Redlich-Kwong. Now these two are those like that have been solved by the different scientists. So then what they did is that they tried to make their own assumptions. But here you can see that there will be only two constants, like the a and b in the van der Waals also, but they have their own different values, and this comes by taking the different assumptions. So we are not going to derive that entire equation, but what I'm showing it to you is that this equation directly. So what Rohit Kelvin called ideal equation state corresponds to and what Swirl-Illich form. So you will see the difference mainly will be arising in this the A and the B values, not in more than that. So in Swirl-Illich form, the another parameter will come into account is the alpha. Okay, and alpha we have been given up by this equation. So this all I have been like derived, and they are not just like they have put the random values. So all this equation has been derived properly, and its explanation is already given in the reference books. So it's better that in examinations, in some of the examinations, what they will do is that they will try to give up your this equation, and just you have to, they will also use sometimes the values of a and b constants. The only thing is that you need to identify which equation you have to use and which the proper like stepwise manner to solve the equation. Okay, so this is the third, and the last one is Pang-Robinson equation of state. This is the fourth one. So the non-ideal equation of state for the Pang-Robinson is given like this, somewhat like this. So it's P equal to RT upon V minus B, and here also there are two different constants. You can see there are A, B also here, B also here, and B also here. Sorry guys. So here also we have two different constant values corresponds to the Pang-Robinson equation of state and alpha value also, because alpha is coming up here, and alpha accounts for the non-spherical systems also in some of the cases, that is corresponds to omega. Okay, so you just need to take care of these equations that have been mentioned in the questions to solve at a particular point, because these equations are not that easy to solve by handy manner, because if they give some of the like gases, non-ideal gases, if they give ammonia and methane, they have shown given you two mixtures of gases, so they have given one gases, and they will give you some pressure and temperature, and they wanted you to derive the like some, they will give you some random vessels, like this vessel is like 30-meter cube size, calculate the pressure that will be developed at this point of time. So that at that time you have to assume that this not assume, but they will be mentioning that this is non-ideal gas, and they have to use non-ideal equation of state, and they will also mention which non-ideal gas equation of state you have to use. So like I said, like we have shown, these are the four non-ideal gas equation of state. The first is van der Waals, second is Redlich-Kwong, third is Swirl-Illich-Kwong, and the fourth one is Pang-Robinson. Okay, so this four non-ideal gas equation of state you please keep in mind, apart from the ideal gas equation of state. So we'll try to solve some of the numericals related to this in the upcoming lectures also, plus today we'll try to solve up one of the numericals related to the simplest one, that is van der Waals equation of state. Okay, apart from this, what has been covered earlier till now is that we'll just see. So for so d of nu equal to Td ns minus Pd Nv. So in terms of molar properties, we can du equal to Tds minus Pdv. Similarly, I can write enthalpy H equal to U plus, because this thing I am just revising, E equal to U minus Ts, and G equal to H minus Ts. So H is enthalpy, A is Helmholtz energy, and G is Gibbs free energy. And we have the corresponding equation like Maxwell relationship. So this can also be derived. You don't have to mug up. It's just the partial differentiation or putting all the values. Okay. And if we do the partial differentiation, what will happen is that del U by del S. Okay, we'll directly show the Maxwell relationship instead of deriving up here, because this can be derived directly. So we'll show the Maxwell relations. odd equations. So there are four different relationships: del T by del V S equal to minus del P by del S at V, del P by del T at V equal to del S by del V at T, del T by del P S equal to minus del V by del S at P, and del V by del T at P to minus. So these are the Maxwell equations. So just it's like I showed in the last week one and a week, not week one, it's week two and week three, thermodynamic property relationships and Maxwell relationships and thermodynamic values. Just like knowing what is Gibbs free energy, atmospheric energy, enthalpy, entropy, and different terms, and just doing partial differentiations related to that. And you should know what is the work done. The work done is the pressure applied to the volumetric difference. So W is equal to integration P dV, and integration will be in the terms of V1 to V2. Okay. So this is not what we have already covered, but I just mentioning it just for like recap. And we have mentioned the partial diffusion of enthalpy Cp dt plus minus T del V by del T at P dP, and entropy is Cp dt by T minus del V by del T at P dP. Okay, so this is already what we have used in the previous thing. Now the main thing is that the some of the terms that we have not covered till now is one of the terms known as the compressibility factor. Sorry guys. Sorry guys. So the term which you now cover is the compressibility factor. So this is given by the symbol Z, and it is PV by RT. So what we'll do is that if you take some of the terms, okay, we will not solve further anything related to write it right now because it will complex at a later point of time. Okay. So what we'll do, we'll try to solve some of the MCQs and everything. Just I'll sync it again. Sometime it will start to lag because of this. Sorry guys. I'm just syncing it with another device so that just a minute, we'll try to sync and it will come up again. Okay, so this is question 1. So we'll try to solve some of the numericals related to this week. So we'll try to cover some of the concepts that we have discussed in the starting of the session, and then we'll try to cover up the later ones. So the first question says for PVT curves, like we've shown the PVT diagram of the ideal fluids and PVT diagram of ideal gases, for a pure substance that I already showed. The quality is 0. So it's called the quality is 0. So if you say the quality, so if you suppose quality is supposed to be X, is equal to the number of moles of vapor of liquid plus number of vapor, and the quality is 0 for pure substance. So if you say the saturated liquid line, the number of vapors will be 0, that is x equal to 0. And there is also a term that is called the quality factor Q in mass transfer. So that is like if you take a saturation line, Q will be equal to 1. Similarly, in terms of like chemical engineering thermodynamics, we define the quality X as by the formula, the number of moles of vapor by number of moles of liquid per number of moles of vapor. But if you take for pure substance, we will consider it as a saturated liquid. Okay, so this is considered as a pure substance. Pure substance, and the quality is 0, because quality is 0, the pure substance will have only pure liquid, there will be no vapor, so the vapor number of moles of vapor will be 0. So only thing that left here means 0 pi number of liquid will be 0 equal to x. Okay, so the quality factor will be 0 for saturated liquid line. So what I did is that, because I know for the saturated liquid line then quality, so I know the formula for the quality. Now I know there are two different terms, vapor and liquid. So if I take each and everything, saturated solid line will consist of the mass, there will be no mass here, saturated liquid and saturated vapor. So for saturated liquid line, that is the quality factor will terms about, there will be a pure substance. So the saturated liquid line, number of moles vapor included will be 0. So we can directly solve, and it's just like quick 1 mark question, not more than that. Okay. So I've given the explanation for that up here also. So it's same like the quality X is given by number of moles of vapor by number of moles of liquid plus number of moles of vapor. It is like a ratio of both the terms. Okay, so the for saturated liquid line, number of moles of vapor equal to 0, that is X equal to 0. Okay, so the simplest one is saturated liquid line as the correct answer. Okay, so now we'll solve the next question. So this is question 1. This is question 2. So now Gibbs-Hellman's equation provides the effect of. Now the Gibbs-Hellman's equation provides the effect of which thing? So they have been given like 4 different MCQs. The reason why I'm taking this question up here is that I've shown you what is Gibbs energy, what is Hellman's energy is equal to H minus TH and A equal to. So I mentioned up here, it's like I'll show you. G is equal to H minus TH and N equal to U minus. This is Gibbs free energy and this is Hellman's free energy. So okay, so they both have different, represented by the 2 different terms. So one is G, Gibbs free energy, that is this, and this one is Hellman's, what has been given, Hellman's free energy. Okay, so what has been asked to us is that, yeah, so we'll try to solve out. So Gibbs-Hellman's equation, now I'm not showing the Gibbs-Hellman's equation, but I will see G is equal to H minus TS. Okay, or I can write this at G by T is equal to H by T minus S. Okay, I have divided it by whole divided equation by T, it will give like this. Or I can do partial differentiation del of G by T at constant with respect to the temperature, constant pressure is equal to del of H by T constant temperature with respect to temperature and pressure minus with respect to temperature at constant pressure. Okay, now what I will do is that I will try to simplify this equation and come up to a point. So what will happen is that, so this will remain the same, I can take the temperature outside, so what will happen is 1 by T, this will be the same, 1 by T del H by del T at P minus del S by del T at P. So this corresponds to, so this is Cp, del H specified constant, Cp by T minus Okay, we have to do two times of partial differentiation, right? So there will be another term h minus h by t square minus h by t square minus cp by t. Okay, so what will happen is that if I take this and try to, so it will be del of del g by t del t at p equal to minus delta h by t square. Okay, so this and this cancel out, and there will be change in the enthalpy respect to the constant. So the correct answer for this one is the change in the temperature on the Gibbs free energy. So this is the correct answer. Okay, so it's just like if you know what is Gibbs free energy, Hermann's energy, then it's much more easier. You have to do the partial differentiation change. This change is mentioned, and you have to do differentiation and try to like simplify that equation. So yeah, this is the same thing like how I've solved right now. So I've given in the form of like a printed form. So since g is equal to h minus ts, I've divided whole equation by divide by temperature. Then I'll try to simplify and do the partial differentiation. You can see all the partial differentiation with respect to temperature and constant pressure. And then I'll try to take some of the common terms outside, like T will come outside, and this corresponds to Cp, this corresponds to Cp by T, Cp by. So this has been derived from the relationships of thermodynamic web, as well as this is the definition of specific heat at constant pressure, that is del H by del T at constant pressure, that is specific heat at constant pressure. And this term has been derived from the Maxwell property relationship. This one. This is specific heat at constant pressure, Cp, and this is derived from the thermodynamic web relationships. So you can see these two terms cancels out. The only term will be remaining is minus h t by t square. So it will change the temperature on the Gibbs free energy. So the correct answer is P. Okay. Now question third. So what they have given is that using the ideal gas law. So this is the simplest one. The same can be solved using the van der Waals equation of states only if that A and B van der Waals constants have been provided to us. So since we have only have to use this van der Waals ideal gas equation of state, all to use that we will mention ideal gas EOS. Okay, so PV equal to nRT. And what they have mentioned is that calculate the volume occupied at two number of moles. So this is N, this is temperature, and this is pressure. Okay. So the volume equal to nRT by P. Number of moles is 2. Universal gas constant is 8.451. Temperature is 300 Kelvin. Pressure is 100 bar. So I will convert into the Pascal. 1 by square 10 to 5 Pascal. This comes out to be 0.499 10 to minus 3 meter cube. So if you see the answers, it will like this, because this is 10 to minus 4. It's just like it's mentioned up here. It's like printed mistake. So it will be in the form of like this thing, minus 3 minus 3 minus 3. Okay, so the correct answer is this. So it's just like I have mentioned in the form of printed form. So PV is equal to nRT and volume is equal to nRT by P. Suppose in the same question if they ask the molar volume. So what is the molar volume? So volume will be volume divided number of moles. RT by P. So you can derive the molar volume also, that is term is by saying this symbol. Okay. Correct answer is this one. So we'll go with the question fourth right now. So it's like the PV behavior of an ideal gas, like we discussed in the last week also. But here we'll go through some of the diagram that has been given to us. So what is given is that is a PV diagram for a pure substance. So we have been given with the PV diagram. This is pressure volume diagram for a pure substance. okay, is represented by the following figure. Then match the following column 1 with the column 2. So now this figure we have already shown in the last week, that is on week 3. So now we have to identify which these lines corresponds to, which these lines correspond in specific terms to. Okay, so they have given like line A, B, C, D. So line A, B, C, D corresponds to an isotherms. Like I said, there will be different isotherms line it will go in. So from this point, if it goes, it's known as the critical point. So it will say T equal to Tc, and T greater than Tc, and T less than Tc. So we have already seen some of the this like isotherms in the previous week, and we have like different curves that will be going. If the temperature is equal to the critical point, it will pass through this point. If the temperature is greater, it will pass through like this, and if it lies this, it will fall inside. Okay, so it we have seen like different isotherms. So the line ABCD is known as an isotherm. So A line XBY. So XBY corresponds to the XBY. So line XBY is correspond to the saturated liquid. So this is a liquid line. This is liquid plus vapor mixture, and this is you can say vapor line or saturated vapor. So XBY corresponds to the saturated liquid line. Line YCZ corresponds to the saturated vapor line. And line BC is known as a triple line because it forms between the two different phases and it's known as a triple line. Okay, so the correct answer is D. You can see A 3 4 3 2 1. Okay, understood. So this is just like some of the points in the exams. I don't know whether this some questions will be there or not, but it's just like in the form of an answer cue. If it has been asked, you can quickly, if you know the concepts of like purity behavior of gases of the pure substances such as pure water or any fluid substance, then it's better you will get 2 marks easily, 2 to 5, not 5 marks, 2 marks or 1 marks easily, because if you know that this corresponds to the isotherm line, this line corresponds to the temperature greater than the critical temperature, and this line corresponds to temperature lower than the critical temperature, and all the three different phases will be involved. First with the saturated liquid phase, mixture of liquid and vapor inside, and the outside will be the another, that is the saturated vapor phase. Okay, so this is what like this purity behavior corresponds to. Okay, so this is how what I've been shown. So the first line is known as a saturated liquid line. This is one is known as the critical point, that is critical temperature, or is known as critical pressure PC. It's known as the critical point. So I will mention it as a critical point. Okay, and the second line is known as the saturated vapor line. The phase between is known as a saturated triple point. And this is known as the isotherm. Okay, so move to next question and try to solve this with the non-ideal equations. So we first go through the question what has been given to us. So it's like a tank of 5 meter cube of the volume is given 5 meter cube. It's filled with weight, that is 10 kg of ammonia at 500 Kelvin. Determine the pressure exerted by ammonia using the ideal gas law. First we have to find out the pressure using the ideal gas equation of state. Second, we have to assume that ammonia obeys the Van der Waals equation of state, and we have been given with the Van der Waals constants A and B, and R value is also given. So we have to find out the pressure between both the equations. First is ideal gas, second is non-ideal, and we'll try to compare both of these values, which is higher and which is lower. Okay, so we try to solve it out. First we'll write what is given. So the temperature is given to us as 500 Kelvin. Volume is, temperature is 500 Kelvin. Volume is 5 meter cube. Mass is 10 kg. Okay, so what will the molar mass of ammonia? We know that NH3 is 17 kg per mole. So molar mass of ammonia, that is S3 is equal to 17 gram per mole. Okay, or you can written write as 17 into 10 is to minus 3 kg per mole. Okay, so what will the molar volume? We have the molar mass and volume. What will the molar volume? Molar volume with the, so we have given 5 meter cube volume of the tank divided by the number of moles. So what will be this thing? So number of moles will be given weight divided by molecular weight. 17 into 10 is to minus 3. This comes out to be 588.235 moles. Okay, so this equal to molar volume will be 5 divided by 588.235. Okay, so this will comes out to be 8.5 into 10 is to minus 3 meter cube per mole. Now first case, so we will type case 1. We have two different cases. So first one is using the ideal gas equation. The PV is equal to nRT, therefore equal to RT by molar volume. R is 8.31451 into 500 divided by molar volume is 8.5 into 10 is to minus 3. So the pressure comes out to be 0.489 into 10 is to minus 3 gives about 10 is to 6 Pascal. Okay, so this is the first pressure which we have found out using the ideal gas equation of state, and case 2 corresponds to the Van der Waals equation, which is given by P is equal to RT upon V minus P minus A by V square. So we have been given P equal to 8.31451, temperature is 500, volume is 8.5 to 10 is to minus 3 minus B. So we take B values as 0.037 into 10 is to minus 3. So 0.037 into 10 is to minus 3, and E values is given to us as 422.546 into 10 is to minus 3 whole divided by 1 square. So it is 5 10 is to minus 3 whole square. Therefore pressures corresponds to 0.485 into 10 is to 6 Pascal. Okay, so we have like two different values for the pressure. One corresponds to so the one value that we have found out from the ideal gas, we assume there is no assumptions, and one we have found out is in the Van der Waals equation set, in which two assumptions are there. One accounts for the attractive forces, that is A, and B accounts for the volume in the system. So we can see both the values, and the value of what you can say non-ideal gas equation of state is lesser compared to the ideal gas, because in ideal world the values what we get will differ, not than ideal cases, because we have ruled out that assumptions, and there will be two different things we have to consider which have not been considered in the ideal gas equation of states. Okay, so this is the first one, and I have given the detailed solution. So this is the first one using the ideal gas equation of state, P is equal to RT by V. The second one is Van der Waals equation of state, that is P is equal to RT upon V minus P minus A by V square. Okay, and we have matched the equations also. So solve another one. So this question, yeah, so here what they said is to using the interval determine the pressure exerted by the nitrogen. Okay, okay, so this is one like just a similar one, but the thing you have to measure is another thing. So determine the pressure exerted by nitrogen using Van der Waals equation of states at temperature of 300 Kelvin and a volume of 5 meter cube per mole we have been given universal gas constant, Curie temperature, and the critical temperature and the critical pressure. So this is T, this is PC. Okay. So, so what we'll do is so now we know Van der Waals equation of state P is equal to RT upon V minus P minus A by V square. But we have not been given A and B, but have given we know Van der Waals constants A and B, but we don't have been given their values. But what they have given additional in this question is a critical temperature and critical pressure values. So we know that A is equal to 27 R square TC square by 64 TC and B equal to RTC by 8PC. So what you have to do is to put directly the values of TC and PC in the constants A and B and find out the values. Now, if okay, and then you have to directly put the values of A and B here. So A is here, B is here, volume is already given to you, there is 5 meter cube, R and T already here, then you can find out the pressure easily. Okay, so this is nothing, just to identify if you have not been given A and B, how to calculate their values. If you know their Van constants corresponds to, and they have given already the critical temperature and critical pressure values. So first find out the A and B value, Van constants values, and then put the Van der Waals constant values in the Van der Waals equation of state, and then you can determine the pressure. Okay, so this is like what I said is the calculated values. So this is Van der Waals constant A and this is Van der Waals constant B. Put both of these values into this equation, that is Van der Waals equation of state. Okay, it's just the simplest one. Just need to think it a little bit. If A and B values are not given, how will you able to identify the pressure using the Van der Waals equation of states? Okay. Move to the seventh question. So let's first see what they have been given. So if 1 mole of an ideal gas at 298 Kelvin undergoes a reversible isothermal process where the molar volume of the gas changes from molar volume, that is 0.023 meter cube per mole, to 0.041 meter cube per mole, what is the entropy change associated with the process? Take R as 8.34 joule per mole Kelvin. Okay, what is the entropy change associated with the process? So we know that entropy S equal to Q by T, or I can write as ds equal to q by t. Q is hq is equal to du plus pdv by t. Therefore, now for an ideal gas, an internal energy U is a function of temperature only. Like this is what we have solved in the terms of like one of the MCQs in the previous weeks. So, and another, we have been given a reversible isothermal process. So for isothermal, so for an isothermal process, the change the energy is internal 0 and ds equal to pd by t. Now we have been given for 1 mole of an ideal gas. So PV equal to nRT, nx1, so PV equal to RT, and we have ds equal to, so if you put du equal to 0, it will be pd by t, and the entropy change is given by delta S equal to R ln V2 by V1. Okay, you just have to integrate this equation and just use this equation in this form. Insert, instead of P we can write RT by V. Okay, put this equation in the integrating this one, We arrived at a final equation as the change in entropy is RLN V2 by V1. Now we have like the molar volume V1 and molar volume V2. We have R, then you can determine the change in the entropy of the system easily. So this is V1, this is V2. We are given with R value. You can finalize the answer. Okay, so this is like simple terms. But if you don't know the concepts of entropy, enthalpy, internal energy, and similar, there will be different terms coming up from like Gibbs free energy, Helmholtz free energy. It will be difficult to like try to begin with the question itself. So don't try to mug up anything. Just try to remember like the fundamental terms. What is enthalpy? What is internal energy? How they are related to the work functions, pressure, temperature, volume, and how they are interrelated using the thermodynamic pair and their Maxwell property relationships. Once you know these things, then it will be easier to arrive at a particular point of time, a particular point of an answer. That okay, you know, like okay, these assumptions I have to make to finally like try to find the question, arrive at an answer. Okay. So this is the thing that I mentioned up here. So we take the enter PV is going to for one mole of an ideal gas, and you can derive this equation. Just you have to put P equal to RT by V and derive and just partial differentiate. So this will be 0 for an isothermal process. So it will be PD by T and PV equal to RT. So put P equal to RT by V and just partial differentiate. So ds will be P is equal to RT by V dV by T. We have to do the partial integration of this equation. You will get this way. Okay. And you have to put directly the values what has been given, that is molar volume 1 and molar volume 2. Okay. So question 7. Try to go to further questions. Now this is a similar one, but try to go through the question first. So consider the following reaction at 1 bar. So they have said consider the following reaction at 1 bar and 298.15 Kelvin. So we have been given an ammonia reaction with hydrogen chloride and the forms an ammonium chloride NH4Cl, that is solid. So the two gaseous molecules combine in order to form a solid product. And that the enthalpy change of reaction and entropy change of reaction has been given to us, that is del HR and del SR at 1 bar. So this is the pressure and this is the temperature in Kelvin. Comment on the feasibility of the reaction. Okay, so if I see for feasibility, the criteria is delta G should be less than equal to 0 at constant temperature and pressure. Now what we'll do, G is equal to H minus Ts, so we'll write minus T. So we'll try to put minus 176.2. This will be plus 298.15, 0.285. This comes out to be 91.22 kilojoule per mole, which is less than 0. So the reaction is feasible. So the criteria is the change in the Gibbs free energy should be less than equal to 0 for the reaction to be feasible at constant temperature and pressure. And we know that G is equal to Gibbs free energy equation, G is equal to H minus Ts. So the change in the Gibbs free energy can be written as delta G. For the reaction, delta GR is equal to delta HR minus T delta SR. This one. Okay. Just have to put the values of enthalpy change of reaction and entropy change of reaction. If you find out the change in the Gibbs free energy of reaction is negative, that is less than 0, the reaction is feasible. If it's positive, the reaction is not feasible. So the reaction, the correct answer is B, that is feasible. Okay. So these are the small points that you guys have to remember at some point, because in the bigger problems it will come at a certain section of that problem. Okay. Now what we'll do is that we'll try to solve some of the problems similar to this, but not an answer we type. Directly we'll try to solve out. Okay. So okay, we'll go. So this is the just like given. So for constant temperature pressure, the criteria is delta G less than 0. So we'll just use the equation G is equal to H minus Ts, like I told you. The change in the gas-free energy for the reaction can be given by delta Gr is equal to delta Hr minus T delta Sr. That is the change in enthalpy of reaction minus change in entropy of reaction at constant temperature. Will give the change in gas-free energy of the reaction. If it's negative, it is less than 0, the reaction is feasible. If it's not less than 0, it is positive, that is greater than 0, the reaction is not feasible. Okay. You can see the value comes out to be minus negative, so the reaction is feasible. Okay. So we have been given this thing. So the PVT relationships of for gas is given as P minus P equal to RT. Okay. So what they ask is that what is del S by del V at T equal to. Okay. So if you see, so what we'll do, we'll take to try to the this equation I will try to differentiate. So and del S by, now we'll take the Maxwell property relationships equal to P. So what we'll do is del S by del P at T is equal to. So if you try to differentiate this equation, partial differentiation of P with respect to T at constant volume, so V minus B is equal to P by T. Okay. So it will be V minus B by R. That is L by del T at constant pressure. This is what it equals to. Just like if you know, so this is what we have mentioned through the Maxwell relationships. So this is Maxwell relation. Because in question we have been given equation related to some sort of like modified Van der Waals equation of state P into V minus B equal to RT, and they've asked what is the partial change in entropy with respect to the volume at constant temperature. So if you know the Maxwell relationships, this term is related to this term to the Maxwell relationships. And if you know this thing, the only thing is to do is to take P by T. So this will be P by T equal to V minus B by sorry, R upon V minus B. And just you have to do the partial differentiation rate of constant volume, it will come the final answer. Okay, so that you can do easily. So this is another question we'll try to solve out. So the thing is given as the PVT relationship for nitrogen is given as P. So the similar equation PV minus B equal to RT, and they have been asking what is. Okay, so for nitrogen the constants A and B are given. B is given and a specific heat Cp, specific constant pressure is given. It undergoes an expansion of 20 bar at theoretical volume 2. So this is P1, P2. Expansion means reduction in the pressure. Okay, so this is P1, P2 and temperature T1, T2. The enthalpy change for this process. So they have been asking the enthalpy change for this process rounded up to the first decimal digit. Okay. Now enthalpy is given by dH. Now we have already given this equation. So it's already derived. I'm not going to derive it again and again. Now we have been given this equation. We try to simplify. We try to partial differentiate. Okay. Now what we'll do is that V minus T del E by del T P equal to V minus T R by P to P. Therefore, the change in the enthalpy will be, this is Cp dt plus Vdp is equal to Cp dt is T2 minus T1, dP is P2 minus P1. Okay, so this is, we have arrived at a final equation. You just have to put your values up here. Got it? There is nothing I've done, is just I've simplified the equation in terms of change in the enthalpy in order to find out what is the change in enthalpy of the process if the process is going in under expansion, and we have been given like initial pressure, final pressure, as well as the initial and the final temperatures. Okay, you just have to put T1, T2. So this is T1, this is T2, this is P1, this is P2, and Cp has been already given to us, and B value is also there. Just put all the values into this equation. You will find out the change in the enthalpy, that is d delta H or dH. Okay, that's the final answer. Now, okay, so this is the last question for today. So we have been given the change in the entropy in joule per mole Kelvin for the process in question 2 rounded up to the 1 digit after decimal point. Okay, so the same question we have to solve the change in the entropy. So what we do is that the change the entropy. So we have, so this question also, this equation also I have given during the starting of the session, dt by t minus value by del t dp, given that p v minus b rt. Previous question. Okay, so what we will be having, we will try to simplify. This is ds equal to cp dt by t minus r by p dp. Okay, so this is change in the entropy. So what we have given, T1, T2, we have given P1, P2, we have already R and Cp. So you can directly put all the values here. You can determine the change in entropy. Okay, so we have used the same equation. The change in enthalpy is given by this. The change in entropy is given by this. We try to simplify this equation using the equation that is P is equal to V minus V RT, and partial differentiated and arrive at the final point. Okay, so this is just like putting all the values into the equation and that finding out the change in enthalpy, change in entropy of the systems. Okay, so like this is what I have for today, is that we try to solve various things related to uh, what you call as non-ideal equation of states. So we have seen all the four non-ideal equation of states. First is Van der Waals equation of state. Second is Pang-Robinson. Third is Redlich-Kwong. Fourth is Redlich-Kwong. And we have shown numericals only related to the Van der Waals equation of states as of now for today's live interactive sessions. And we have seen the change, how the change in enthalpy, entropy of the system can be related to the non-ideal equation of states, and various numericals and the MCQs related to that. Okay, so from the next week, what we'll do is we'll try to cover up some of the other non-ideal equation of states. We'll try to solve some more numerical problems related to that, how the various constants A and B can be found out, what difference we can find out using the different non-ideal equation of states into the different problems, because in the questions in the examination, sorry, they will try to find out the variation in the pressure, why there is a variation in the pressure if you find out the pressure value using the different ideal gas as well as non-ideal equation of state. Then you have to know what are the assumptions that has been made for solving that equations and that thing. Okay, so this is what I have for today. So if in case you have any issues related to like any of the numerical problems that we have been solving during these live interactive sessions or anything, please do let me know. We will be able to solve as soon as possible before if the due date has been ended for assignments, we will try to sort it out. If not, then I will take some of the questions from the reference books or the some tutorial problems which we have already done. And if you have any issues related to the tutorials, also please also do let me know tutorials, assignment problems, or any concepts that has been covered during the entire week. Please do let me know in that this live interactive session is done. Okay, so for today, if I think so, if there are no more questions, we'll meet next week on Saturday. It's from 3 to 5 at the same time for this live interactive session. So feel free to reach me out, and you can even post your questions on the NPTEL Swim portal. There is a feedback forum also. You can mail them also if you have any issues related to the assignments or the tutorials. And also let me know during this live interactive sessions if you face any issues related to some of the problems or the tutorials or some assignment problems, so that I will be able to help you guys before the final examinations begin. So what I will be doing is that we have been covering starting from the beginning of the chemical engineering thermodynamics, and we're building up our fundamental skills. So that's why I'm not just putting directly the MCQs, but we're trying to solve out the numericals, which has been has the concept that has got during that weekend only. Okay, so that if you have gone through the week notes, like week lectures, and we'll try to see this live interactive sessions, I will try to solve out that numericals only, which have the concepts covered during the entire week only. So that you will try to brush up the concepts. If you don't know, you can just go through 1 or 2 hours of lecture contents and again come back and see this live interactive session, because all of these things will be uploaded into the Swim portal along with this PPT in the form of a PDF format. So everything will be made available to you guys on the NPTEL Swim portal. Both the things will be there: YouTube videos, this video link in MP4 format, plus this PPT in the form of a PDF. So you can access all the things. Thus, what I recommend is that before uh, uh, like doing anything, just try to go through the lecture notes first that has been given on the Swim portal, and then try to solve out some of the unsolved numericals. First, go to the discussions what we are discussing in this live session and this online lectures, and then you try to solve out some of the numericals on your own, unsolved numericals. Then you will build a confidence. Okay, yeah, so this is what I'm lagging at behind, and we need to ask these questions in the next weekend during the live practice session, so that I can help you guys and try to rectify that issues as soon as possible. Okay, so if there are no any further problems or questions, we'll meet next week. Thank you guys for joining this session. Thank you. See you next week, Saturday, same time, 3 to 5. Please do let me know any questions, any queries related to the same concepts what we have covered till week 4. Okay. See ya. Thank you for joining, students. Thank you. Take care. Bye bye.